What will be the next mode of vibration in a closed tube? I don't know whether you can actually see this. Now, in the next mode of vibration, let me just reset my camera a bit. Alright, I want to refocus the camera a bit to show you the picture on the right. There we are. Okay. Now, the second mode of vibration, remember the fixed end is a node, the open end is an antinode. So in the next mode of vibration, you can have an antinode and a node inside the tube. Tell me, how many waves are there inside the tube? How many waves? Now, you can see the distance between an antinode and a node is 1/4 of a wavelength. That means there is 1/4, 2/4, 3/4 of a wavelength inside the tube now. So what is the relation between the wavelength of the wave inside the tube and the length of the tube? The whole length of the tube now contains 1/4 plus another quarter plus another quarter. There are 3/4 of a wavelength inside the tube now. Therefore, we can say, since the distance between a node and an antinode is 1/4 of a lambda, the whole length of the tube now contains 3/4 of a wavelength. That means L, the length of the tube, is 3/4 of a wavelength. Therefore, what is lambda equal to? Lambda equal to 4L divided by 3. Alright, let's now find the frequency of this mode of vibration. The frequency of vibration of this mode is F equal to V over lambda. Our lambda is 4L over 3. And that will be, this 3 will go up. We get that's equal to 3V over 4L. But if you remember, look at this. The fundamental frequency is V over 4L. So this V over 4L is the fundamental frequency. Therefore, in the next mode of vibration, the frequency equal to 3 times the fundamental frequency. That means, you notice one thing, you cannot get twice the fundamental in a closed tube. You get the fundamental frequency. The next mode of vibration in a closed tube is 3 times the fundamental, the third harmonic. In other words, there is no second harmonic in a closed tube. Alright, if you now look at the diagram on the right, this is the third mode of vibration. In the third mode of vibration, of course you have an antinode at the mouth, a node at the closed end, then you have an antinode, node, antinode, node inside. Tell me, how many waves are there inside the length of the tube? You can go like this. The distance between an antinode and a node is 1/4 of a wavelength. 1/4, 2/4, 3/4, 4/4, 5/4. There are 5/4 of the wavelength. That means the frequency of this vibration, if you do the same thing as I showed you previously, you will find that it will be 5 times the fundamental. That means if F0 is the fundamental frequency, in the next mode of vibration the frequency will be 3 times the fundamental, and in the next mode the frequency will be 5 times the fundamental, the next will be 7 times the fundamental, and so on. It means all even harmonics are missing from a closed tube. The fundamental is the first harmonic, and the frequency of the second mode actually is the third harmonic. This is the third harmonic. only odd multiples of the fundamental are found in the closed tube. All even harmonics are missing. What a pity, is that right? Closed tube does not give us any even harmonic. Let's now look at open tube. What is an open tube? An open tube, by definition, is open at both ends. So, if the tube is open at both ends, look at the fundamental mode of vibration. An antinode has to be at both open ends. An open end cannot have a node. That means a node has to be at the middle. So the fundamental mode of vibration in an open tube has an antinode, a node, and an antinode. Alright? Now, the tube contains how many wavelengths? Can you tell me how many wavelengths are in the tube? The distance between the node and an antinode is a quarter wavelength. So this will be 1/4 wavelength plus 1/4 wavelength will be half of a wavelength. The length of the tube now contains half of a wavelength. So we say L equal to lambda by 2, or lambda equal to 2L. Let's write down an equation for the fundamental frequency of the open tube. The fundamental frequency in an open tube can be written as, alright, F0 equal to V over lambda, and that lambda equal to 2L, and that will be V over 2L. So, the frequency of the fundamental is, did you see that? I just changed the screen very quickly. What is the frequency of the fundamental in an open tube? Will be V over 2L. The frequency of the fundamental is V over 2L. Now, look at the next mode of vibration, second mode of vibration. There you have 1/4, 2/4, 3/4, 4/4 of a wavelength inside the tube. In other words, the length of the tube equal to one wavelength. Wavelength equal to the length of the tube. Therefore, the frequency of this mode will be, again, frequency is V over lambda, lambda equal to L. So the frequency of the second mode of vibration is V over L. Tell me, what was the frequency of the fundamental? V over 2L. Can you write this in terms of the fundamental? Yes, because V over L is 2 times V over 2L. So the frequency of the second mode is 2 times the fundamental. You see, you have the second harmonic there. Now the frequency of the third mode in a similar way will be the third harmonic, 3F0 and so on. What does that mean? It means in an open tube there are no harmonics missing. Open tube will give you the fundamental, the first harmonic, the second harmonic, the third harmonic, and so on. So if you want to use a tube to construct a musical instrument, for example, which of these tubes will you be preferring? It has to be an open tube. Why don't you want to use a closed tube? Because a closed tube gives you only odd harmonics. Even harmonics are missing. Now, do you know a musical instrument that uses the resonance of air columns inside a tube? There are many musical instruments. A flute, a piccolo, all these are examples using open tube. Now, is there a flute using open tube? Yes. Both ends are open. One end you have the reed where you blow, the other end is open. And you can change the length of the tube. Remember the frequency of the fundamental is V over 2L. L on the denominator. That means as the length increases, the frequency decreases. A very long tube will produce a very low frequency. If you want to produce very high frequency, you go for very short tubes. All right. Let's now talk about musical instruments, of course. Musical instruments make use of this